doesn't interfere with any of you. And yeah, just 1 second. I need to bind here with the live. Now we're live supposedly. Okay. And just 1 second that I want to mute. Doesn't interfere with the other one.
I see. I see only panelists, right? I don't see.
No, you can also hit, if you hit the participants, you will see the participants. You know, you have like, so far there's like 81 people there.
Okay, okay, good.
And then there's about 30 people or 40, 35 or 40 people in the other one. And they usually show up almost on time. Nowadays, everything with Zoom is like right on the money.
Right. Okay, that's good.
So let me begin if you don't mind. So you see now the presentation here, and then so thank you. Welcome back all to the online SPICE-SPIN+X seminar series that I lead here myself, with Angela Wittmann in SPICE, together with Karen Eversosite, which is also connected to SPICE, but now in Duisburg University, in collaboration with the Collaborative Research Center SPIN+X, that is led by Martina Schliemann and Burkhard Hillebrands in Kaiserslautern, and Matthias Chloe here in Mainz. Just a reminder, this is a Zoom webinar, so the participants only see the panelists or hear the panelists, but you can also chat with everybody. That would be not one-on-one, but you can chat directly, or please write your questions on the Q&A, and I will give you the floor or promote you to panelists to ask to the speaker directly. They're usually on at this time, as they all know, and it's at the same time synchronous with this YouTube channel that will be immediately posted afterwards. And please check the next few talks. Sometimes, like on the 25th, there will be no talk, but next week we have Juan Carlos Rojas Sanchez, for example. So today's speaker is very well known in magnetism and material science. Sang-Wook Cheong is the director of the Center of Quantum Materials and Physicists in Rutgers, has been a professor there for a long time and works on physical functionalities in complex materials, particularly connected to collective correlations and collective phases transitions, mesoscopic self-organization in solids, and many of these things having to do with oxides and metal oxides and topological matter and multiferroids. He has many awards. It has a long, very distinguished career. I like this one, that is the most influential scientific minds, as I've known from having watched some of his talks in the March meetings often, and also the McGroody Prize for New Materials of the APS, which is also a very reputable one in 2010. Together with other ones that I have listed here. So with that, I'll stop sharing, and then I will ask Sang-Wook, please, to go ahead and share your screen and start your presentation whenever you like. And we're looking very much forward to your talk.
Can you see my screen?
Yeah, we can see your screen. Perfect.
Okay, good. Thank you very much, Jairo. My great pleasure to give this presentation. So I'll discuss about magnetic chirality. That's the title. But what I'm going to discuss is what chirality can do on magnetism. Okay, next. Okay. Oh, there we are. Okay, so let me go back here. So this beautiful flower is something called Wisteria in New Jersey, in the US, where I am. Now we have these beautiful flowers. This is a vine. So the stem of this vine tree, there's this twist. So this has chirality. And as you know, many solids, they do have this kind of a twisting. So they do have a chirality. That's something I'm going to discuss today. So this term chiral or chirality is very popular, always popular in chemistry. So chiral molecules, they have a twist, and also things like chiral chemical reaction and chiral separation, things like that, very popular in chemistry. Now, somehow, last few years, 5 years or so, this chiral or chirality became very popular in physics. So it's used for everywhere, like this. So chiral surface space chiral anomaly and chiral magnons, chiral phonons. So chiral everything. So what does this mean? And that's something I'm going to discuss today. So for that, we have to go through these symmetry operations just to fix notation. I is a space inversion, T is a time reversal, R is rotation. I discuss mostly two-fold rotation. So that's R, and M is mirror. Most often, I ignore translation. So my talk is based on these papers, these 5 papers. So people involved in this work are more or less authors of these papers. But these 2 papers are most important for this presentation. One is this Beijing Huang, and the other one is Xiang Shu. They are main contributors for this talk. So for this presentation, I need to introduce this concept of something I call SOS, Symmetry Operational Similarity. So here idea is rather simple. So we try to measure something. So sample is here, and then we have an experimental setup that includes sample environment, like we apply magnetic field, electric field, or strain to the sample. And also we have a measurable, something we are trying to measure. So we put all these things right-hand side. I call this experimental setup. So if the sample has the same symmetry with experimental setup, then this experimental setup, with this experimental setup, this sample can show that non-zero or measurable. That's the idea. So this SOS relationship has 2 important aspects. One is left-hand side. In other words, sample can have a lower symmetry than right-hand side. It cannot have a higher symmetry than right-hand side. That's one. Second one is it's permutable. So we can move around these things. For example, a sample environment can be left-hand side, like this B relationship and C relationship. Sometimes this measurable and sample environment, we can switch around this. So this is a permutable relationship we can have. And this is a closely related with this old concept, something called Newman's principle or Curie law. So chirality, let's define that first. The chirality means, so we have a spring or screw like this. The original image and mirror image, they cannot overlap to each other with any spatial rotations freely allowed. So I call free rotation. That means we can allow this any spatial rotation freely when we consider certain symmetry is broken or not. So because of this, in general, we have this inversion equals mirror times two-fold rotation. Since we allow free rotation, we can ignore this city rotation so that inversion becomes now same with mirror refraction. So chiral object having all broken mirror symmetries, inversion is also naturally broken. So this chiral object, they show, probably most of you are familiar with something called optical activity, natural optical activity. So linear polarized light going through chiral materials, light polarization can rotate, something called natural optical activity. It's closely related with Ferro rotation. So Ferro rotation, ferromagnetic system, linear polarized light coming to the sample, and light polarization does rotate. And this aspect is, in fact, it's all due to this fact that circularly polarized light is chiral. In other words, if you have a circularly polarized light like this, left kind, if you do mirror refraction, now it becomes like that. So now it becomes a right kind. So they cannot overlap to each other with any free spatial rotation. So circularly polarized light is chiral. This is the reason why we do have this natural optical activity, as well as this Faraday rotation. so that this circular polarized light can couple with chirality readily. Here I'm talking about structural chirality, crystallographic chirality. That's beautifully demonstrated in this recent paper. This CRC Kimura's group has done this on this long name compound. The structure is chiral, so that it does have chiral domains. Let's say this bright region is right kind of chiral domain, and the black region is left chiral domain. Now, if you shine laser circularly polarized light, then we can they were able to manipulate this chiral domains. You can see that in this video. So laser going through this dark region now becomes bright region. So chiral domains can be controlled with circularly polarized light. So this is a beautiful demonstration that circularly polarized light is in fact chiral. So this chiral object can have this very relevant, interesting SOS relationships. They do have a permittable relationship. So A, B, and C. So A is in chiral object. If you apply magnetic field, this whole left-hand side has the same symmetry with K. K is like a velocity or linear momentum or like a wave vector. Again, it's permittable so that we can switch this K and H, and then we have this B relationship. Now we can put all K and H in right-hand side. We can have also this C relationship. So all these relationships, they correspond to particular physical phenomena like this. So let me first discuss this A case. It's relevant to something called NDD effect, non-reciprocal directional dichroism. So what it means is like this. This left-hand side has the same symmetry with velocity vector K. Then if you have some symmetry operation switching from K to minus K, since the left-hand side, right-hand side has the same symmetry, that particular symmetry operation, switching K to minus K, has to also influence this left-hand side. What this means is if you have a left-hand side, let's say this kind, this top kind, then K and minus K, the reaction can be different, so that it can be directional dependence it can show. So it's a so-called non-reciprocal directional dichroism, NDD effect. So that can be shown that moving object, this velocity vector can be pretty much anything. It can be electron, spin wave, phonons, or light, or it can be actually its own sample motion. So this shows a spin wave. So in this chiral magnetic system, if you apply magnetic field, then spin wave in zero magnetic field, minus K around the zero, plus K, they are symmetric. But if you do apply magnetic field, it becomes asymmetric. So for example, like if you apply 10 Tesla, then minus K around the 0 point, minus K plus K, they are very different. So this difference is due to this NDD effect. That's with spin wave. Similar thing can be done with light. So light moving sample, this chiral system, this nickel thorium oxide, light is going through this chiral material. Now you apply magnetic field, and then you switch light propagation direction from plus K to minus K, then absorption spectrum changes like this. So blue one corresponds to this plus K, and this red one corresponds, red one corresponds to this plus K, and blue one corresponds to minus K. There's this difference. This difference is due to NDD effect. That's with light. Now, this twisted bilayer graphene is very popular, but this twisted bilayer graphene is chiral. In other words, all mirror symmetry is broken. It does have a crystallographic chirality, so that it should show natural optical activity as well as magnetochiral effect. Magnetochiral effect means this NDD effect in chiral system in the presence of magnetic field. In fact, that's we kind of predicted in this 2020 paper. A twisted graphene layer, bilayer is chiral, so exhibit a natural optical activity, and also should exhibit non-reciprocal optical and also transport effects in the presence of magnetic field, which need to be experimentally verified. So after this paper, this 21 paper, in fact, they observed this unidirectional magnetic resistance in twisted bilayer graphene. So that corresponds to this NDD effect of electrons, this transport. This optics should also exhibit something similar, but because it's so thin, probably difficult to do optical experiment, but probably eventually one should be able to do that. Now, something I call Ferro Rotation, I'm going to discuss a little bit. So if you have, let's say, electric polarization or dipole rotating around like this, in my presentation, red arrows are electric dipoles or electric polarization, and blue arrows spins or magnetization. So electric dipole move around like this. So it's very much like this yin-yang symbol. If you do mirror refraction, then becomes this right-hand side symbol, or polarization rotated in opposite direction. However, in this case, if you flip this, two-fold rotation around this axis, this left-hand side becomes right-hand side, so that this is not chiral. This is in fact achiral. So this achiral, something we call Ferro Rotation. Now, what is interesting is now this itself is again mirror symmetry is not broken, and this is inversion symmetry. Inversion symmetry is also not broken. However, now if you do apply electric field like this one, so let's say this symbol as yin, the other symbol as a yang. If you apply electric field, then this combined object now, because of this applied electric field, now inversion symmetry is broken, so that now this has the same symmetry with this chiral object. If this is like a left chiral object, then this is the other one, same electric field or direction, but yang, then it becomes right kind chiral object. So that this, when you apply electric field, this ferro rotational system should exhibit, for example, like natural optical activity. Then we predicted the part, so that effect, by applying electric field and optical rotation occurs, there's something called linear optical gyration. So we proposed the possible use of linear optical gyration is suggested as a way to detect ferro rotational domains. It was done in this 18 paper. So 2 years later, this group has done this beautiful experiment in NTO. This is a ferro rotation system. So there can be clockwise and counterclockwise ferro rotational or yin and yang type ferro rotation domains. And now they apply electric field, and then they did natural optical rotation, and they were able to observe ferro rotation domains like this. So by changing polarization direction, this contrast reversal, they also observed. So in fact, this technique, what we proposed, beautifully works in this ferro rotational system. Now, this spin rotating like this is something I call helical spins. Some people call this a proper screw type spin holder. This helical spin, if you do mirror refraction, now this left kind helical spin becomes right kind helical spin. You cannot overlap to each other. So this is a chiral. So again, this blue arrow means spin. It's rotating. This is chiral. Even though this is a kind of a magnetic ordering, however, time reversal symmetry is not broken here. That's important. So time reversal symmetry should not be broken in chiral object. That's the case in this helical spin state. So we propose this magnetic helicity, so helical spins, that has associated with structural chirality, so it may exhibit optical activity. It was in this 19 paper. 2 years later, there is a science paper. They did exactly what we proposed. So they observed natural optical activity in helical magnetic state. So that's exactly what we proposed. They were able to even switch this helical spin state. So far I discussed the three kinds of chiral objects. So structural chirality, helical spin state, and then ferro rotation combined with electric field. They are all chiral, and time reversal symmetry is not broken. However, all mirror symmetries are broken. And they have this three kinds of SOS relationship. And A type we discussed. Now let's move to B type. So B type, what it means is something moving in the chiral sample should show magnetic field or magnetization. So this in the same direction. So I call this diagonal current-induced magnetization. That was in fact observed in this chiral tellurium system. Tellurium, single element tellurium solid, has this kind of crystallographic chirality. So there, even though it's a non-magnetic, if you apply current, electric current, then induced magnetization was detected by using this NMR. So it's that B-SOS relationship beautifully works in this system. In fact, this old paper, they observed something similar, even though they didn't quite understand why this happens. But the reason is because of this B-SOS relationship. This tellurium also shows this magnetochiral effect. In other words, you apply magnetic field and you measure its transport along magnetic field direction, then plus K minus K shows a different effect. So some kind of a diode-like NDD effect was also observed in this recent paper on chiral tellurium. Now, C is also very interesting situation. So C relationship. So H and K combined, it has the same symmetry with chirality. In fact, that's also related with this. So if I go back here, so if something moving in chiral system, it can have magnetic field or magnetization. In fact, this natural optical activity can be understood exactly with that SOS relationship. In other words, in chiral system, light is coming. It has K. Because of that, magnetization is induced. That magnetization couples with this angular momentum, so that it does show, in fact, Faraday rotation. So what I'm trying to say is that natural optical activity is a kind of a Faraday rotation due to magnetization induced by optical light itself. And that view has never been discussed as far as I can tell. So I think that's the same phenomenon, but it's quite different view, and that can be understood in terms of this B-SOS relationship. Going back to this slide, so this is also relevant to this parity symmetric breaking in cobalt 60. So probably some of you are familiar with this old paper, Madame Wu, this very important experimental work on cobalt 60. There's beta decay. When there is a beta decay, electrons is emitted. And when you apply magnetic field on this cobalt 60, this electron K, motion, electron velocity, this K, if you do mirror refraction, this H direction does not change. However, K direction does change. So these two should be symmetric if symmetry is not broken, but she found there is a difference. So they call this P symmetry breaking. So this is a very much origin of all this symmetry breaking concept in high energy physics. After this, this P symmetry breaking, and after that, CP symmetry breaking was also discussed. But I tell you this, after all these years, again, this was discussed in terms of parity symmetry breaking, but as far as I can tell, this is not really simple parity symmetry breaking. This is chirality symmetry breaking. Chirality symmetry breaking. In other words, the right-hand side is chiral object, and that symmetry is broken. So it's a chirality symmetry breaking. Because of a chirality symmetry breaking, of course, parity or space inversion is also broken. But as far as I can tell, that's not the dominant effect. The dominant effect is chirality symmetry breaking. One can also do some interesting, similarly relevant experiment for solid. So this system is chiral, it's a metallic, crystallographic chiral is metallic system. And they do show this very interesting chiral domains. So left chiral domain here, right chiral domain, they are coming right next to each other. And then in fact, the 6 domains are merging to one point, something we call the 6 vortex. So there are 3 kinds of left chiral domains and right kind of 3 right kind of chiral domains. They merge one point from this vortex. One is vortex, the next one becomes anti-vortex. These chiral domains, if you do now spin polarized tunneling experiment. Now we have a tunneling current using magnetized STM tip. So this tunneling current is now spin polarized. So it has now this H and K combined object coming to this chiral object. Then this chiral object touching this sample having either left chiral domain or right chiral domain, they have a different tunneling magnitude. So that's exactly because of this C-SOS relationship that we have observed. So we have only one kind of this right-hand side, spin polarized tunneling current, but we have a left or right kind of chiral domains. They show different tunneling current magnitude. They show contrast. So this contrast is because of this C-SOS relationship. We can switch this. So from this chiral object, now we can switch to this helical spins. Then same thing should happen. So what it means is this helical spin state can be controlled by having simultaneous electric current and magnetic field. And if you switch one of them, let's say magnetic field, then preferred domain becomes a different kind of helical domain. That they beautifully demonstrate in this paper. So in this metallic helical system, now they can apply magnetic field as well as current. If you do have a simultaneous magnetic field and current, then you can simultaneously, you can control this helicity of this metallic system. At high temperature, above, excuse me, above magnetic transient temperature, the system is a central symmetry. It becomes chiral only below magnetic transient temperature through helical spin state, so that this, there should be left and right kind of helical domains. They can be controlled by the simultaneous presence of a magnetic field and electric field. This is due to this C-SOS relationship. Okay, so let me skip this part. It has been almost 30 minutes, so let me skip this part. This is also relevant, but going back to this, so as I mentioned, this circularly polarized light is chiral. And some of you may know something called vortex beams, vortex light beams. So certainly, vortex light beam is light having, so circularly polarized light is light with spin angular momentum, but vortex light beam has orbital angular momentum. So that vortex light beam is also certainly chiral. Now, let's think about this linearly polarized light. So linearly polarized light can be represented like this. So it has K. In second direction, there is electric field. Third direction, there is this magnetic field. They are all perpendicular to each other. Now you do mirror refraction on that. If you do mirror refraction, K direction does change, E direction does not change, H direction does change. If this is a left kind, this one is also left kind. So linearly polarized light is not chiral, it's achiral. So it's interesting that sometimes people think chirality is the same with handedness. The light has definitely, it does have a handedness, but this is not chiral. In other words, handedness can be different from chirality. So that's one important aspect. Another important aspect is this. Just like this light, this topological insulators and topological surface state became very popular last 5-10 years. And people do call this surface state as, so surface state, there is this spin momentum locking. And this surface state, people call this chiral mode or chiral surface state. So if you think about just one K, so somewhere here, then there is a surface electric field, and then there is electron K. Spin locking is along this third direction. So the situation is very much like this light. In other words, this surface state is not chiral, it's achiral. So in this sense, this terminology is incorrect. Now, we discussed the helical spin state is chiral. Now, let's discuss different kind of spin rotation, cycloidal spin. So spins are on this screen plane, but rotating like this. So in this case, if you do mirror refraction, it becomes like that. If it is clockwise, the other one becomes also clockwise. So the cycloidal spin state is achiral. So in contrast, we discussed that this helical spin is chiral. And this also, many people kind of use this term confusing way. But black type ferromagnetic wires, they are like a helical spin, so it is chiral. However, near type ferromagnetic wires, it's like this cycloidal spin state. So near type ferromagnetic wires are achiral, it's not chiral. And also the SPICE, magnon and ferromagnetism is very much important. Ferromagnetism is very much important. And a number of people discuss this simple ferromagnet, magnons are chiral, but that's not true. It does have this rotating component, but if you do this mirror symmetry operation, you can show easily. That's all shown on this screen, in this slide. I cannot go through these details, but if you do mirror refraction, certain mirror symmetry is not broken. So magnons in simple ferromagnet is not chiral. You may come up with some crazy anti-ferromagnetic case, some chiral situation, but in simple ferromagnetic system, magnons are not chiral, it's achiral. And so this term became very popular, this chiral phonons, but I'm sure I tell you that this is also not chiral. It's not chiral, but it does produce magnetism. So I think probably the right terminology is magnetic phonons. The idea is very simple. If you have a non-central symmetric system, like this guy shown here, like let's say boron nitride, single layer can be like this. If you have a K coming along this direction, this blue arrow direction, not red arrow direction. So blue arrow is like this K direction. Then they can induce this magnetization along this outer plane direction. So it does produce magnetization with K type phonons. So that's why some people call this dynamic multiplericity. Some other people call this chiral phonons. I call this magnetic phonons. What is important, what I want to emphasize here is that this object is not chiral. Now let's move on. So now we discuss about some interesting kind of spin texture, like spin rotating like this. So again, blue arrows are spins. So this A is spin rotating. It's called toroidal moment or magnetic toroidal moment. Right hand side D is magnetic quadrupole. So this case, they do exhibit off-diagonal linear magnetoelectricity. So what it means is if you apply electric field this direction, then magnetization along this perpendicular direction, off-diagonal direction, can be induced. In fact, this left-hand side object, toroidal moment combined with electric field does have S with magnetization. So in fact, it does show magnetization. So it does show off-diagonal linear magnetoelectricity. If it is this opposite rotation, but same electric field, then of course induced magnetization is now in opposite direction. In other words, this is a linear with each direct, or this whether it's clockwise or counterclockwise. So sign is fixed by that. So this case, the mirror symmetry is not broken in the following sense. If you do mirror operation, mirror is shown here. So mirror is on the screen, then this object becomes that object. it's this mirror image. But if you flip this around this axis, this becomes that one. So that in that sense, mirror symmetry is not broken. So this blue column is mirror symmetry is not broken. Same thing here. If you do blue, this mirror operation, then this becomes that. However, if you flip around this axis, then becomes the other one. So that this is mirror symmetry is not broken, so it's not chiral. But now if you add some Cantillon moment, it becomes different. So for example, like here, if you have this toroidal moment in the AB plane on the screen, if you have a Cantillon moment along C direction or same direction Cantillon moment, then if you do mirror refraction, becomes the other object, and by any spatial rotation, you cannot overlap this one and that one. So that this is now becomes all mirror symmetries are broken. So now it becomes chiral. Here, what is important is even though this is some kind of magnetic order, but if you do time reversal operation, and then if you allow free spatial rotation, then time reversal symmetry is not broken. So the blue color here means T is not broken. And same thing here. Now this magnetic quadrupole moment combined with alternating spins. So spin up, spin down, spin up, spin down. If you have these alternating spins, this also becomes chiral. Mirror symmetry is broken, time reversal is not broken. This object, so center part, so we have a rotation, center part is into the plane, outside is out of the plane. This is also chiral. If the mirror symmetry broken, time reversal not broken. Of course, this is standard skirmion, so for the black type skirmion. So all of this, black type skirmion and this object, this E, and also that object, D, they are all chiral. All mirror symmetries are broken without breaking time reversal symmetry. In fact, this object is the D-type, ferro toroidal moment combined with Cantillon moment was observed in this barium cobalt silicon oxide system. It's not square lattice system, it's triangular lattice system, but still has this rotation combined with Cantillon moment. So this object is chiral. Structurally, this is chiral, and magnetism develops at low temperature, and magnetically, this is also chiral. But what is interesting is this is chiral, but if you consider only in the AB plane, it's off-diagonal linear magnetic electric. So for example, if you apply magnetic field, then polarization can be induced like this. If you can switch these two, because it's permittable. If you apply polarization along this electric field along that direction, then magnetization can be induced in that direction. So it does show off-diagonal linear magneto-electric effect. If you consider only in-plane component of this chiral spin object that I'm discussing. Now, in this system, in this barium cobalt system, in fact, there are three different magnetic sublattices. And two of them, so red one and this dark blue one, toroidal moment is the same direction. Toroidal moment is the same direction, counterclockwise. This light blue sublattice, spin rotation, toroidal moment direction is now opposite. Now clockwise, it's opposite. So in terms of a total toroidal moment, we have a -2 plus 1. Well, let's say +2 to plus -1, so the total toroidal moment is like +1 in zero magnetic field. But it does have a Cantillon moment. So if you apply a magnetic field along C direction, out of plane direction, then this Cantillon moment can be flipped to one direction. Cantillon moment in zero field is also this 2-to-1 ratio with opposite direction. So Cantillon moment is also like a +1. But if you apply magnetic field, it becomes now +3 Cantillon moment. At the same time, toroidal moment becomes also like a +3. So this toroidal moment can be controlled by magnetic field. That's quite interesting. So when that happens, this magneto-electric effect also switches from 1 to 3. That will be beautifully observed in this system. So by using external magnetic field along C direction, in-plane toroidal moment can be controlled so that the in-plane off-diagonal linear magnetic electric effect can be also controlled by external magnetic field. So we can change from +3 toroidal moment, +1 toroidal moment, plus 1, -1 toward the moment, -3 toward the moment. When that happens, off-diagonal linear magnetic electricity beautifully follows this magnitude of toward the moment and also direction. So that concept beautifully works in this system. So that's something we discuss about this D. Now E is also realized. E is also a very interesting case. Don't have much time, so let me just tell you this. But this quarter of moment in the AV plane combined with alternating C direction moment, plus C minus C plus C minus C. This is a chiral, or symmetry is broken without breaking time symmetry. In terms of magnetic point group, this is a 4' to 2'. It's a chiral, and it's a non-ferromagnetic. There is no net moment. This structure, magnetic structure, was in fact observed in this compound, in this complex system. I have to tell you, actually, this was a mistake. This is a mistake. Compound name is different, even longer than this one. It does contain lead, but different, also tellurium, but it's a different compound. Sorry about this mistake. It's a long name compound, but that's in this paper. So anyway, in this compound, which is structurally chiral, but below magnetic transit temperature, it does show this very interesting magnetic chirality. And because of that, it shows a very interesting physical property that I do not have time to discuss. And these two objects, so toroidal moment combined with canting moment along C, and then quadrupole moment combined with alternating canting moment, these two, all these different kind of characteristics listed here. Chirality I discussed, magnetic moment, toroidal moment, scalar chirality, vector chirality, octupolar chirality, all kind of listed here. But one thing I want to emphasize is this chirality, the way I defined. This is a left, there is also a left, but none of these others has a same property like this chirality. So they are very different. Very often, some people think scalar chirality is the same with the chirality, but that's not true. Chirality, scalar chirality, they are different. Okay, so that we discussed. Now, now I'm going to discuss the cases where mirror symmetry is broken and also time reversal symmetry is broken. So this simple case is this I. So I is spin pointing all out, was all pointing in. So it's like a magnetic monopole. So magnetic monopole, if you do mirror reflection, these two direction does switch, so it becomes like this. So N-type magnetic monopole becomes S-type magnetic monopole if you do mirror reflection. Same thing with time reversal. Time reversal, this becomes that one, obviously. So this case, time reversal as well as mirror symmetry is a broken magnetic monopole case. So this, when this happens, then so mirror symmetry is broken. So this red means broken, mirror symmetry is broken. So this case, when time mirror symmetry is also broken, then it does show diagonal linear magnetic electric effect. In other words, you apply electric field this direction, same direction, induced magnetization can be observed. Of course, we can switch these two, it's permittable. Same thing here. So this case, if you have this S-type rather than N-type, then same electric field induced magnetization will be opposite direction. So it does show diagonal linear magnetic electricity. So this kind of object, having all broken mirror symmetries and also time reversal symmetry broken, I call this chiral prime. Prime usually for magnetic point group, prime means time reversal symmetry is not broken. Unbroken time reversal symmetry they use for prime, but in my definition, prime means time reversal symmetry is broken. So most well known diagonal linear magnetic electric system is a chromium-203. Chromium-203 is a complex system, can be represented with this simple cartoon shown here. So in that case, if you apply magnetic field, polarization can be induced. If you apply electric field, magnetization can be induced. It does show diagonal linear magnetic electric effect. So in this case, T is broken, and so all mirror symmetry is broken. So this is in fact C prime, chirality prime. In fact, it turns out that all linear, diagonal linear magnetic electric systems are C prime. Now, we discussed about Ferro rotation or natural optical activity, similar with similar with those. So those experiments are through transmission, optical experiment through transmission. But one can do similar experiment with reflection. So that's a mock experiment, magnetic optical co-rotation. So mock experiment, linear polarized light hitting the sample and reflected light has a polarization, light polarization rotation like this. So polarization rotation clockwise, counterclockwise, these two experimental setups can be linked through those symmetry operations, mx mirror, mirror, x mirror, y, and then time reversal. What it means is if you break this symmetry, all of them, if you have this broken all of this symmetry, then there can be non-zero Mach effect. Very often people think Mach is all something to do with ferromagnetism, only ferromagnetism. That's definitely not true. Of course, ferromagnetism, this symmetry is broken, so it does show, they do show Mach effect. However, even without Canting moment or net ferromagnetic moment, this symmetry can be broken. This Mach effect can be shown. In fact, all linear magnetic electric system, in fact, all C prime system does show, or C prime does show Mach effect. Okay, so so this something I call chirality and then chirality prime, C or C prime. They are very different objects. They show very different physical phenomena. And but this C prime case I discussed so far, like chromium 203 or this magnetic monopole. If you do so mirror symmetry is broken, in other words, inversion is broken, and so time symmetry is broken. However, they are broken in the same manner, so that if you do inversion times t, time reversal, then symmetry is unbroken. So all the situation I discussed, they have an unbroken I times t, unbroken I times t. Now, in general, that's the case, by the way. So magnetic monopole is like that. And so this is having some Canting moment like that, Canting moment like this, or a situation like this. So this, you probably realize this error situation is like near type magnetic skirmion. Near type skirmion is time reversal symmetry is broken, so that this is not chiral, it's a chiral prime. So time reversal symmetry is also broken. That's important. Now, in general, this C prime having broken time reversal symmetry can have a unbroken I times t, like these cases. Then they show this diagonal linear magnetic effect or Mach effect. And also, it can have a broken I times t. So those point groups do have a broken I times t. So this case, it has more broken symmetry than these two cases. So this I call type 1 C prime, that I call type 2 C prime. So type 2 C prime has more broken symmetry than these two, so that this case, it exhibits both of these effects. These two, they are very different objects and they exhibit different physical phenomena, but this type 2 C prime shows both this effect as well as that effect. Okay, so I may be a little bit early. Okay, so here is a conclusion. Okay, this is a conclusion, but since we have a little bit time, maybe I'll go back and I'll discuss something I skipped, if you don't mind.
Yeah, no problem at all.
Okay, good. Okay, so here. Okay, so as we discussed this Ferro rotation combined with electric field. Ferro rotation combined with electric field has the same symmetry with this chirality. Now it's permittable, so that now we can move this electric field in this direction, right-hand side direction. So they have the same symmetry. Now I can switch this structural chirality with magnetic chirality like helical spin. So we have now this relationship. Now this electric field, now I can also switch by strain gradient. Spatial variation of a strain has the same symmetry with electric field or electric polarization. so that so here rather than electric field, I can have a strain gradient. So some of you may be familiar with something called flexoelectricity. Flexoelectricity means when you bend, in other words, when you have a strain gradient, you induce polarization. That's simply because they have the same symmetry. In other words, strain gradient and then polarization, they have the same symmetry. So that if you apply strain gradient on helical spin, that's just like a helical spin, you apply electric field. Okay, then what happens? So when you combine this, it should be like this Ferro Rotation in principle. That in fact we observed. So if you have a helical spin along Z direction, if now strain gradient, we apply strain gradient a little bit kind of a special way, but this case relevant vector is also along this direction. So let's say strain gradient along this Z direction combined with helical spin, it has same symmetry with this yin-yang symbol, in other words, Ferro Rotation. In fact, that does result in this kind of spiral magnetic superstructure. So this very large scale, this is a very small scale. This is a macroscopic scale. Spiral magnetic superstructure is observed. That's exactly what happens in helical spin system. So helical spin system, if you have this strain gradient, then much large length scale, like order of 100 micron length scale, this kind of beautiful spiral magnetic superstructure can be observed. So that can be also understood in terms of this SOS relationship. Okay, so that's the one I skipped. So I have now conclusion slide. Okay, so conclusion slide. I discussed about what chirality can do on magnetism. Three kinds of magnetic chirality state I discussed. Helical spin state, toroidal moment plus cantilever moment. Third one is magnetic quadrupole moment combined with alternating cantilever moment. Again, this is very much interesting. I had a early, very limited discussion, but this is also a very interesting case. The last one is a black type skirmion. As I discussed, near type skirmion is not chiral. This magnetic chirality shows natural optical activity, magneto-chiral effect, in other words, non-reciprocal directional dichroism in the presence of a magnetic field, and also it shows this current-induced magnetization. Chirality prime, there are two different kinds. Type 1 is I times T symmetry is not broken. It shows this diagonal linear magnetization effect as well as Mach effect. So I emphasize all linear ME system, diagonal ones, they are supposed to show Mach effect, not just a simple ferromagnet or having net ferromagnetic moment showing a Mach effect. That should work. In addition, any linear ME system having even no net ferromagnetic moment should also show Mach effect. Type 2 chirality prime means mirror symmetry is broken, time reversal is broken, and also I times T is also broken. So since it has additional broken symmetry, it exhibits both this effects as well as those effects. Okay, so that's the end of my talk. Thank you very much for your attention.
Thank you very much. I'll give you an applause from the audience. Very interesting overview of what chirality means and what maybe some of the concepts that we have been misnaming or thinking about. Is some questions that come in mind. So please, the audience, raise your hand and I'll promote you to directly to panelists to ask your questions to the speaker. The panelists that are already raising their hands. So Matthias, if you don't mind, go ahead and ask your question.
Okay. Yeah. First of all, thank you a lot for the wonderful talk on chirality. I have one question regarding the magnons. You showed one slide where you showed the magnon and said that magnons are not chiral. And you showed a picture there of a magnon that was a very specific type of magnon, right? It was so-called Damon-Eschbach geometry, where the static magnetization is orthogonal to the propagation direction, right? And I fully agree that that is not chiral. However, if you look at a backward volume geometry, where the magnetization direction is along the propagation direction, I think that these magnons are chiral.
Okay, somehow my presentation, do you see my screen?
Yes.
Okay, it keeps doing it by itself. Okay, I don't know what's happening. Okay, sorry about this. I don't know what is happening. Okay, that's good. Okay, so yeah, that's exactly what I mentioned. You know, this the one in Kittel's book, right? Simple ferromagnet, how magnon propagates. That is, it does have this rotating component and also this. So you see my hands, right? So the spin simple ferromagnet magnon propagation is like this. So it looks like there is some kind of a rotating component and also this big, spin component. So it looks like chiral object, but however, again, if you do all this mirror symmetry operation, it is not chiral. Okay, so that particular case is not chiral, but I'm sure one can come up with some chiral situation. First of all, even the ground state without magnon, just the ground state can be chiral. That's the whole point of my talk, right? Magnetic chirality, certain magnetic state can be chiral. Okay, so those chiral systems, of course, excitation will be chiral. And but even without ground state chiral, so certain excitation could be chiral. It's possible. Certainly, it's very possible. But so certain, for example, like some anti-ferromagnet, some spin fluctuation could be chiral. But what I want to emphasize, many people made this statement: simple ferromagnet magnons are chiral. That's not true.
Okay, so but if you go, can you show that slide again? With the,
I'm trying to find that.
Or you can show the one with the helical spin spiral.
Yeah, I have a difficult to. Okay, so let me see. I think it was after this, right?
Yes.
What I recommend is if I find the slide, I strongly recommend you take a picture of this, or it'll be on the online anyway. You take a picture of this and you try to do this symmetry operation yourself. Okay, and you'll be convinced.
Yeah, no. I'm fully convinced that this specific spin wave that you show here is achiral. I completely agree. But if you go one slide back, that's good. Most people don't. Most people don't. No question about that. But if you go one slide back, I think it was one slide back or one.
This one.
Yes. So a backward volume wave, spin wave. It looks like what you draw here for the helical spin state, but just dynamic, right? That's basically a spin wave that propagates like this. Okay. And I think that this magnon is chiral because the helical spin state is chiral.
Okay, it could be, but one has to be careful. It looks like propagating, but since this is a static, what you're discussing has a time component.
Yes.
Time component. We have to sit down and we will have to go through this symmetry operation, especially time reversal. Okay, especially time reversal. You have to determine whether T is broken or not broken. I cannot do it right here, but I think you can do it. I can do it. So it's very important to check whether time reversal symmetry is broken or not. This state case time reversal symmetry is not broken, even though it's a magnetic state. But when it's moving, dynamic case, whether it's broken or not is very much important.
Okay. Yes. Okay. That's something we have to check. Yeah.
Okay. Good. Yes. Let's check that. We can communicate after that. I can also check that.
Okay. Thank you.
Yeah. Okay. Thank you.
Sumit, go ahead and ask your question, please.
Thank you for this wonderful talk. I have actually three questions.
Three. First, okay. I have to write down. Okay.
Or I can repeat. Don't worry about it.
Okay. Let's do one by one. Okay. How about that? So that I don't have to write down.
Fine for me. First question. Could you comment on the relation between helicity and chirality in this case?
Okay, good question. Very good question. Okay, so chirality is mathematically well defined. In fact, that's exactly what I have done in this seminar. Chirality is mathematically well defined. Okay, helicity is mathematically not defined.
I see.
You can use as you wish. Helical spin, helical, original, my understanding is the helical concept came from this high energy physics. Some particle moving, having some rotation, some kind of, angular momentum type. That's how this helical concept came in. Now, so let me emphasize this. So as I said in the beginning, chirality became very popular in the physics community last 5-10 years. Something rotating, something moving around.
Yep.
People tend to call it chiral. But I'm trying to convince you guys that's not the case. You really have to do this mirror operation. Chirality is a well-defined concept. You cannot just abuse this term. Chirality is well-defined. Helicity is not well-defined. Helicity, you can call, for example, like this chiral azimuth in topological system. Definitely, trying to convince it's not chiral, but certainly it can be called as a helical state. Helical, so helical, edge state is the right terminology. Helical, surface state is, I believe, is the right terminology, even though helical is not mathematically well-defined concept. Okay, let's move on.
Okay, sure. The second question would be, you defined what kind of response one can expect if you use an electrical response from a chiral sample or, let's say, optical. But what if I use a spin polarized current? Can there be some difference, or it can be?
Well, that's exactly what I discussed, right?
Yep.
Where was that? So you're talking about kind of a SPICE-STM type experiment, right? That's exactly what I discussed here. So if you have a SPICE-STM, then you have this basically C-SOS relationship. Okay, where is this? Yeah, this one. Okay, so the C relationship, right? If you have a spin polarized, let's say, current or tunneling current, that itself is like this right-hand side object. So it's gonna definitely couple with chiral domains. Because of that, because of that, this chiral object, if you do spin polarized STM on this system, which is chiral, it's not magnetic. It's magnetic at low temperature, but in paramagnetic state, high temperature, if you do SPICE-STM, there is a STM magnitude, tunneling current magnitude is different, whether it's left chiral domain and right chiral domain. That's exactly because of this C-SOS relationship. That's exactly with spin polarized tunneling current.
So in this case, would it be possible to define a spin-dependent resistance in terms of chirality?
Yeah, exactly. That's what this is. This tunneling current magnitude, which is a kind of resistance.
Okay, thank you. And the last question is about dimensionality. So let's say I have a particular system which is chiral in 2-dimensional, and now I want to stack it on top of each other. Could I still preserve chirality, or I would? No. Chirality is defined in 3D. Okay, something I call Ferro Rotation. You may call that, you remember Ferro Rotation, if I flip becomes the other one, mirror image, right? So 2-dimension, you cannot do this, right? It's not allowed. Then the Ferro Rotation is a chiral in 2-dimension, okay? So Ferro Rotation is a chiral in 2-dimension. If you want to define like that, in 2-dimension, all mirror stream is broken. Okay, then Ferro Rotation is like that in 2-dimension. But if you stack them, Ferro rotation, stack them along C direction, then it's still Ferro Rotation. It's not chiral. Unless Ferro Rotation, while stacking, not simple stacking like A stacking. If you do kind of A and then rotate and then rotate, if you do that kind of stacking, of course, then becomes chiral. But otherwise, it's a Ferro Rotation, even if you do simple stacking. Okay, so all 3-dimensional real compound having Ferro Rotation, they are exactly like that. It's the same direction, so that it's not chiral. It's only Ferro Rotation. I see. Okay, thank you. That's all.
Okay, it's all good question. Thank you.
So Angela, go ahead and ask your question, and then.
Thank you so much for this wonderful talk. It's been really interesting. I was wondering, so you were talking about different types of chiral configurations, and then also, different types of chirality with the chiral prime and so on. Whether you could comment a little bit about what kind of coupling you would expect between those different types of chirality, for example.
Well, that's exactly what I discussed, right? The conclusion. So again, this chiral and chiral prime, they are very different objects. It's very defined. One has unbroken T, broken mirrors. The other one has all broken, including T. Okay, so here, okay. So because of that, they have a very different property, especially this type 1 chirality prime. It shows these effects, and chirality shows those effects. So they are very different properties. So this they show these properties. What that means is they have a coupling. Those properties, for example, like a natural optical activity, that means light, linearly polarized or circularly polarized light couples with this magnetic chirality. That's how this natural optical activity occurs, right? So you see this phenomena means those relevant couplings do occur. That's what it means. And they are very different. Again, type 1 C prime and then C, they are very different objects, mathematically different objects, and physically it shows a very different phenomena. And the coupling is very different.
Thank you.
Thank you.
Yeah, I hope that's clear enough. Okay.
Martin, go ahead.
Hello, thanks for this also very interesting and inspiring talk. I have a question regarding this vortex light beam, this light with orbital momentum. I agree with you that can be regarded as chiral, but my question is if it's useful for any interactions, this chirality for any interaction with material, because this vortex beam, that's a spatial variation of the phase of the light beam. So on every point you have then a different phase, but the interaction is maybe sometimes locally, but you cannot use this, let's say, chirality of this beam.
Okay, it's a very important question you're asking. I've been thinking about the last 5 years on this.
Okay.
Even though I just mentioned the one sentence about vortex beam, but exactly what you discussed, what you mentioned, something I've been thinking. It's not a simple question. It's not very simple. Okay. So, this vortex beam is a chiral. Okay, that's number one. And in some sense, it has when you have a larger orbital angular momentum, as you probably know, this orbital angular momentum can be 10,000 times larger than spin angular momentum in terms of magnitude. It can be huge, right? So, in some sense, kind of it can have a big chirality. Okay, compared with just the regular circular polarized light, it has much larger chirality, whatever that means. Okay, because you have a lot of twist. That's what it means. So when you have a lot of twist, then can you have a kind of a bigger coupling, better coupling than simple circular polarized light? Can that happen kind of a local scale, or it can happen more kind of macroscopic scale? Okay, that's all relevant question. So macroscopically, it's more obvious. It should happen. Okay, it should happen so that, for example, like if you have nanoparticles, you probably have seen this, nanoparticles, then, vortex beam comes, the size of this is like 10 micron, vortex, it forms a vortex loop, so-called, with this loop here. You can rotate object.
Yeah,
so this kind of, macroscopic object coupling is obvious. Okay, coupling is obvious. Now, kind of, so local scale, how that's going to happen. So for example, like with vortex beam, what's going to happen with Faraday rotation? Ferro rotation is all something to do with circular polarized light coupling with magnetization, or let's say natural optical activity, same thing. By having this circular polarized light, the vortex beam, can you have a bigger effect? Right, you cannot have something doesn't exist with circular polarized light. Somehow, operator spin can do that. I don't think that can happen, but it can have just bigger effects because it has a kind of bigger chirality. That's all very much relevant and important question. But we have this very initial stage one PR paper published. So at least the ferromagnetic case, it seems like really the signal goes like a magnitude of total angular momentum. Total angular momentum, so L plus S really matters. So large L really helps, even though we got is only like 2 or 3, but we didn't get 10,000. But still, it looks like a signal goes like L plus S. So total angular momentum, spin plus orbital, seems very much important. But even this case, it's macroscopic sample we did experiment. So kind of local scale, atomic scale, whether something can happen. For example, like you can think about some kind of forbidden transition, atomic level forbidden transition, having different kind of angular momentum. Can you induce that kind of transition with vortex beam? It's all important question, but very little has been discussed theoretically and experimentally. And I think it's a very interesting new direction. A lot of things can be done.
You can segue into the guy that is doing Orbitronics, which is Sang-Wook Go. So go ahead. Ask your question.
Thanks, Iro. First of all, thank you very much for a very interesting talk. Actually, I also have a couple of papers on chirality, but it makes me think that I have to check carefully actually what I've meant chirality in my papers. Actually, my question is regarding orbital magnetism, especially current-induced orbital magnetism in chiral crystals, in tellurium crystal that you have mentioned. And in this crystal, the crystal structure looks like solenoid. So if you apply current along this c-axis, and then this circulation of current motion generates orbital magnetism. And the question that I've been asking for myself for a long time is, how can we efficiently measure this non-equilibrium orbital magnetization? And it's actually related to the previous question that I also have read your wonderful papers on vortex beams. And in my review paper on orbitronics, I also cited your papers mentioning that this vortex beam might be a really new way of efficiently measuring orbital magnetism. So I want to ask you what you actually think about measuring orbital magnetism by vortex beam, whether this is going to be more efficient compared to other existing methods such as like a MOOC or XMCD.
Okay. I went through this so fast. Let me try to share my screen again. Okay, so I went through this very fast. So orbital magnetism, let's discuss first, okay? Tellurium.
Yeah.
So you are right. In some sense, tellurium has this kind of twist in the crystallographic structure, so that you may say, oh, so it's like a coil. When you apply current, there is coil. So coil, you have a current, then circulation of current. So there is a orbital moment showing up. What a big deal.
Yeah.
However, at least in terms of symmetry, this has never been done. But there are lots of chiral systems which it's chiral, but it does not have a really this kind of twist. Okay. For example, like this, all the Skolnian system saying it's a so-called cubic chiral system. Like many of those Skolnian systems, they are cubic. It does not have this kind of twist you see in tellurium. However, those systems supposed to, it's not done yet, supposed to show this orbital magnetization if you do have a current. Okay, in principle, at least in terms of symmetry.
Yeah.
So that's one, and there's even more. It turns out that even non-chiral system, in other words, not all mirror symmetry broken, there are cases. Yeah, that's something I could spend next couple of hours. Non-even chiral system, current can induce orbital magnetization. Even non-chiral system, if you break certain symmetries, it can do that. So that's all possible. Okay, so that's possibility. And the second, how to measure this? In fact, this I went through this very quickly. So they did this beautiful experiment, and they didn't know what it really meant, I think. In fact, I was talking with one of the authors. They didn't know what it really means. So it's already a pretty old paper, 1979. So what they did is in tellurium, you apply current. Maybe you're familiar with this paper. You apply current, then they did optical rotation, terahertz optical rotation. So terahertz optical rotation, there is beautiful rotation. This is not natural optical activity. This is a effect induced by current.
Yeah. Yeah.
Okay. Induced by current. So this is the best way you can measure, at least in tellurium case. Okay. Yep. It's a kind of a conducting sample. If it's not conducting, you cannot do this, right? At least the conducting sample, you can apply current, electric current. Then you measure this optical rotation, and you see what happens as function of a current. You switch towards current direction. Then you can check this orbital magnetization. So experimentally, this technique is not that trivial, but still it can be done. Okay, I would say it's a straightforward experiment to do. Okay, okay. Now vortex beam. Okay, so vortex beam again. It's all interesting, all relevant as I discussed earlier, but it's a very limited work has been done. And so, for example, so question is like this. Okay, so in principle, this should be the case. Okay, in principle, any material, let's say a piece of window glass, you shine with circularly polarized light. You're supposed to induce orbital magnetic moment in terms of symmetry.
Yeah.
Never been done, but it's supposed to. Okay, circularly polarized. Again, vortex beam is like a circularly polarized light with a lot of twisting, so that you can induce even larger this magnetization, orbital magnetization. If you shine vortex beam on piece of glass, which is not magnetic, which is not even periodic solid. So in terms of symmetry, it should work like that. And all these things I just discussed have never been done. Maybe the effect will be too tiny to measure, but I'm pretty sure sometimes technique one can measure this tiny effect. In principle, it should be possible. Okay, hopefully that answers your question.
Yeah, actually I understand that this is possible by symmetry, but what I'm worried is actually more about the magnitude of the effect. For example, for current-induced orbital magnetization, in recent experiments, this effect is so small because the effect is induced by current, and by if you measure orbital magnetism induced by current, you measure roughly about 10 nanoradian of rotation from Moog. So I was wondering whether vortex beam can increase this susceptibility.
I think so. I think so. Again, vortex beam has a larger
definitely
chirality, more twisting, so that in principle it should show a bigger effect. That's certainly true. And actually, you said nano something radian. That's really, really small. That's probably even so-called Sagnac technique. Probably that's difficult to measure. But so tellurium case, it has a huge spin-orbit coupling, right?
Yeah.
That probably helps. So they measure pretty large effect here. This case, 10⁻² radian. So probably because of I think there are two reasons. So, one is tellurium, so they has a large spin-orbit coupling. They use terahertz, and somehow in this sample, terahertz somehow shows a kind of enhanced effect. I don't know why. So I think not just the vortex or not issue. I think frequency will be also some kind of energy matching will be also probably important to have a right kind of exactly what resonance. Very poor understanding at this point. But for example, if you have think of something like this. So magnetic system. So for example, like a magnetic chiral system that I discussed, which has no net ferromagnetic moment. Okay. And those systems, somehow, if it's, let's say, conducting enough, if you have a current going through, then, and also if there's a large enough spin-orbit coupling, then that magnetic state itself could produce this magnetization. Never been done. But, that induced orbital magnetization could be significant because you're starting from some kind of magnetic state. Yeah, so that's one thing. But another thing I want to emphasize is something I mentioned briefly. Probably you are familiar with this natural optical activity versus Ferro rotation. But as I said, natural optical activity can be understood as a consequence of this
Induced
might be
magnetization.
exactly
Yeah.
induced magnetization, and then there is a Faraday rotation.
Yeah.
Okay, I think this is a kind of new concept. But with that concept, if there is a big natural optical activity in some sample, basically that means it has a large, induced magnetization. So in that sense, maybe already done.
Yeah. Thank you very much for a very detailed answer.
Okay.
Thank you.
I enjoyed the talk very much.
Thank you very much.
And thank you, Sang-Wook. Fortunately, I have to really run for another meeting. It's been a wonderful talk with lots of very nice discussions, and there were, I think, also the 200 people that showed up today. It was 150.
Oh, really? Okay.
550 on YouTube.
I see.
We need a lot of interest from you, and then we definitely have to go back and take very careful how we define our chirality.
Yeah, exactly. What I recommend to everybody is not too difficult, right? You just do altimeter and then hand it this way, and that way you figure out, what you claim to be chiral is really chiral or not.
Yeah, but I will
strongly recommend
afterwards, because I don't have time today. Regarding to your similarity notation compared to Newman principle, and then but anyway, I'll try to follow it up. But thank you once again, everybody, and please stay safe. And we hope to see you next week.
Okay. Thank you very much. I enjoyed the talk. Thank you.